Imagine trying to draw this, like, perfect, down-to-the-inch architectural blueprint of a house. But you have to do it while sprinting through the hallways, completely blindfolded.
Oh, I mean, that sounds totally impossible.
Right. It sounds like a complete nightmare. But that is the exact mathematical puzzle happening inside a robot vacuum cleaner right now.
Yeah, it really is.
Or, think about when you strap on a VR headset and you physically walk around your living room. You're exploring a digital castle, and you expect the digital walls to perfectly match your real furniture.
Which we all just take entirely for granted now.
Absolutely. Underneath that seamless experience is honestly one of the most maddeningly complex computational puzzles we have ever tried to solve.
For a machine to just, see and move in the physical world without immediately crashing into a wall, it has to perform this constant, high-speed juggling act of probability, geometry, and, well, guesswork.
Okay, let's unpack this. Welcome to the deep dive. Today, our mission is to explore a fascinating technology called simultaneous localization and mapping.
Commonly known as SLAM, S-L-A-M.
Right, SLAM. So for you listening, if you have ever wondered how self-driving cars, delivery drones, or even those augmented reality apps on your phone actually perceive the physical space around them, SLAM is the invisible magic making it all happen.
It's the invisible scaffolding of autonomy, really.
But to really grasp how this works, we have to start with this massive, fundamental logical paradox at the center of the technology.
Yes, the core of SLAM is literally a chicken or the egg problem.
I love that the source material actually calls it that.
I mean, it's the best way to describe it. The paradox is incredibly simple. You cannot navigate an environment without a map. But you cannot build a map of an unknown environment without knowing exactly where you are within it.
It's an endless loop. How do you map the room if you don't know where you're standing? But how do you know where you're standing if you don't have a map?
Exactly.
Going back to that blindfolded house scenario, say you wake up in pitch black. You take a tentative step forward, reach out, feel a wall, and you start drawing a mental floor plan in your head. But because you're blindfolded, your sense of how many steps you've actually taken isn't perfect. Maybe your stride was like a little wider than you thought. So your estimate of your own location is just a very good guess.
Which means the map you were drawing in your head based on that location is also just a guess.
Right. Both your location and your map are nothing more than continuously updated approximations.
And that blindfolded guesswork really highlights the exact mathematical reality that SLAM algorithms have to navigate. They aren't dealing in absolute certainties at all.
They're just guessing.
They are dealing entirely in probabilities. The objective of SLAM is not absolute flawless perfection. The goal is what they call operational compliance.
Operational compliance, meaning it just has to be good enough to not crash.
Exactly. It just has to be mathematically tight enough for the robot to accomplish its task without failing. And the way a machine achieves this is by applying Bayes' rule.
Okay, Bayes' rule. So we're talking about the statistical principle of updating probabilities based on new evidence.
Yes. The system is calculating what we call location posteriors.
Location posteriors. Okay, let's break down the mechanics of how that actually happens for the robot.
Sure. So the robot holds a mathematical model of where it thinks it is and a model of what it thinks the map looks like. Every time the robot moves, it applies a transition function.
Which is just a fancy way of saying it predicts where it went.
Right. It's a mathematical prediction of where it should be based strictly on the commands it sent to its motors. So it thinks, I told my wheels to roll forward for 1 second, so I should be 2 feet ahead.
Okay, makes sense.
Then it takes in new sensor observations from the physical world. It compares what it actually senses to what it expected to sense, and it sequentially updates both its location and the map.
So it's constantly asking itself, given the raw sensor data I just collected and the motor movements I just made, what is the most statistically probable reality?
Exactly. You nailed it.
Doing that once is impressive. Doing it dozens or hundreds of times a second, it's mind-blowing.
Oh, it's an incredible feat of computation.
But wait, this leads me to a major mechanical problem. If SLAM relies on continuous probabilistic guessing, how does the math keep the robot from getting completely lost in its own cascading errors?
That is the million-dollar question.
Because if my mental map in that blindfolded house is off by just 1 inch on step 1, by step 50, I've accumulated so much error that I'm trying to walk through a refrigerator.
That battle against cascading error is literally what drove decades of algorithmic research.
Really?
Yeah. In the 1990s and early 2000s, the dominant method to solve this was the extended Kalman filter, or EKF.
EKS, okay.
Right. EKF SLAM is feature-based. It tries to estimate the probability distribution for the robot's pose, meaning its exact position and orientation, alongside the coordinates of landmarks it sees in the map.
There is a pretty significant Achilles heel to EKFs, though, right? Like,
Yeah.
it struggles the second the real world gets too messy.
Yeah, it completely falls apart.
Yeah.
And the reason EKF fails in highly uncertain environments is that it relies heavily on a Gaussian noise assumption.
Okay, hold on. Gaussian noise assumption, let's translate that.
It basically assumes that the errors or uncertainties in its measurements will always follow a nice, neat, predictable bell curve.
Ah, okay.
But the real world doesn't always produce neat bell curves of error. When a robot hits an unexpected patch of terrain or a sensor glitches wildly, the error is non-Gaussian.
It's messy.
Exactly. The mathematical linearization in the EKF just shatters under that unpredictability, and the robot gets hopelessly lost. So to solve this, the industry moved toward newer methods like graph slam.
Graph slam. And graph slam approaches the map completely differently, right?
Very different.
Instead of just guessing step by step, it uses sparse information matrices and generates a factor graph of observation interdependencies.
Wow, look at you with the technical terms.
I read the source material, but let's clarify how that actually functions, because a factor graph of interdependencies sounds like pure jargon.
It really does.
Are we talking about the robot tethering its memories together? Like if it sees a doorway at minute 1 and then sees that exact same doorway at minute 5 from a different angle, does it realize those two data points are the same physical object?
That tethering concept is the perfect way to visualize it. Imagine the robot's path is a string of nodes, and every time it observes a landmark, it connects a mathematical rubber band between its current position and that landmark.
Okay, I like the rubber band analogy.
Right, so when it recognizes that same doorway later, it connects another rubber band. Graph Slam optimizes all these interdependencies at once.
So instead of relying on a fragile chain of sequential guesses where one mistake ruins everything.
Yes, exactly. The tension of all those mathematical rubber bands naturally pulls the entire map into the most stable, globally aligned shape.
That is brilliant. I have to push back on the physical movement side of this map, though.
Okay, hit me.
We keep talking about the robot tracking its own motion. But what if a robot vacuum's wheels slip on a slick hardwood floor?
Oh, happens all the time.
Right, so it sends a command to its motors to move forward 2 feet. The motors spin perfectly, but the robot actually just spins its wheels in a puddle of spilled coffee.
Right.
The internal computer thinks, great, I'm 2 feet ahead. But physically, it hasn't moved an inch. Doesn't that completely ruin the transition function and the location posteriors?
It's a great question. This is a classic problem in kinematics modeling because movement data is inherently unreliable. The noise from independent angular and linear movements is messy, non-Gaussian noise.
So the system doesn't trust the wheels blindly.
Exactly. Reading the wheel movement is a process called odometry. And the trick to modern SLAM is that it refuses to treat odometry as the absolute truth.
Oh, okay.
It treats the physical spinning of the wheels as just one more sensory input to be heavily scrutinized. It weighs the wheel data against the camera data and the laser data.
So if the wheels say, hey, we definitely moved 2 feet, but the camera says the doorway is still exactly where it was, the algorithm relies on the visual data to realize it slipped.
Precisely. It's a democracy of senses.
A democracy of senses. I love that.
A very heavily weighted democracy, yes. The algorithm is constantly deciding which sense is the most trustworthy in any given millisecond.
Let's talk about those senses then. We know the math can weigh different inputs, but what exactly are these inputs? How does this machine physically perceive the space to feed this voracious mathematical engine?
Well, the hardware side of SLAM involves a wildly diverse array of sensors. At the most data-heavy extreme, there is LiDAR.
Light detection and ranging.
Exactly. LiDAR physically spins and shoots out lasers, measuring exactly how long it takes for the light to bounce back. This creates massive, incredibly dense 3D point clouds of an environment.
It's like a topography map of the room.
Right. And with LiDAR, a system gets so much raw geometric data that sometimes it barely even needs complex SLAM inference. The shapes in the laser point clouds are so crisp they can just be unambiguously aligned on top of each other, frame by frame.
Okay, so if the blindfolded house scenario we talked about earlier is tactile SLAM, just fumbling for a light switch in a pitch black room where your spatial data is incredibly sparse, LiDAR is like flipping on a stadium floodlight.
Yes, you see the exact geometry of everything instantly.
But LiDAR is notoriously expensive, right? And power hungry and bulky. I mean, you aren't putting a spinning laser array on a smartphone.
No, definitely not. which is why Visual SLAM, or V-SLAM, became the industry standard for consumer tech. Visual SLAM uses normal 2D cameras, making it perfect for mobile devices.
And the breakthrough that made VSLAM viable was the invention of SIFT, right?
Yes, Scale Invariant Feature Transforms, or SIFT.
These SIFT algorithms allow a simple camera to extract unique local features from an image, like maybe the sharp corner of a picture frame or the pattern on a rug.
Right, and recognize them regardless of whether the camera is 2 feet away or 20 feet away, in bright light or in shadow. It basically turns raw pixels into mathematical fingerprints.
Mathematical fingerprints. That is so cool. And beyond cameras and lasers, there are incredibly niche ways to map a space too.
Oh, there are some wild ones.
Like Wi-Fi SLAM, which maps the layout of a building based purely on the fluctuating signal strengths of nearby Wi-Fi routers.
Yeah, that one is fascinating.
And my absolute favorite from the source material. There's a kind of SLAM designed for human pedestrians that uses an inertial measurement unit.
Which is basically an advanced motion sensor.
Right. Mounted directly on a shoe. It relies on the biological fact that humans naturally avoid walking into walls.
Hopefully.
Usually, right? So it uses our organic pathfinding to automatically build accurate floor plans of indoor buildings just by tracking our footsteps.
It's brilliantly simple. But, when we look at robots that have to share space with those humans, we see systems like audio-visual SLAM.
Okay, combining audio and video.
Exactly. This fuses camera data with acoustic data. It uses microphone arrays to estimate the direction of arrival, or DUA, of a sound source.
Like human speech.
Right, so the robot can interact with us naturally.
Why do you need to fuse them, though? I mean, if the robot has a camera, why can't it just look at the human who is talking?
Well, the core rule of sensor fusion is statistical independence.
Okay, explain that.
You purposefully want to combine sensors that fail in completely different ways so they can compensate for each other's weaknesses.
I see.
Like, lightweight monocular cameras have a very narrow field of view. They get occluded if someone steps in front of them, and they fail completely if the lights go out.
Which makes sense.
But audio has a 360-degree field of view and works perfectly in pitch black.
But audio has its own flaws, too, right?
Oh, absolutely. It is highly susceptible to reverberation and background noise. But by fusing them, the visual data compensates for the audio echoes, and the audio data compensates for the camera's blind spots.
It's like having eyes in the back of your head that can hear.
That is a great way to put it.
So we've solved how a robot figures out it's in a static room using lasers and cameras. But if I walk through that room, haven't I just ruined its geometric map?
Yeah, the real world refuses to stand still.
Right. People are walking around, dogs are running, chairs get dragged across the floor. How does the math handle a world that is constantly shifting? Like, if a robot is mapping a hallway and I walk right past it, why doesn't the robot just assume I'm a very weird shifting wall?
Well, the system has to separate the static geometry from the dynamic chaos, and this is handled by a model called SLAM with DATMO.
DATMO, detection and tracking of moving objects.
Yes. Essentially, the system is programmed to track non-static entities, like a pedestrian or a moving car, in a very similar way to how it tracks its own location.
Okay.
It identifies that an object is an anomaly against a static background, classifies it as a moving entity, and updates its changing coordinates in real time.
So it basically maintains two separate ledgers, one strict ledger for the permanent walls and infrastructure, and a secondary fluid ledger for the things moving around between them. It
Exactly.
doesn't permanently bake my shape into the map of the hallway.
Thankfully, no.
But there's another dynamic problem we have to talk about, and it feels like the ultimate test of a SLAM system. Loop closure.
Oh, loop closure is arguably the most critical make-or-break moment in a SLAM algorithm's journey.
Because it addresses the problem of recognizing a previously visited location, right?
Yes. Let's imagine a robot is tasked with mapping a giant circular office building.
Okay.
By the time it navigates all the way around the circle and arrives exactly back where it started, all those tiny non-Gaussian kinematics errors, the slight wheel slips, the minor sensor glitches, they've all accumulated.
The compounding errors we talked about.
Right. So the robot's internal math might insist it is 10 feet away from its starting point, even though it's physically standing right on top of it.
Oh, wow.
And because of that accumulated error, the algorithm assigns a very low probability to the idea that it's back at the beginning.
So how does it snap out of that delusion? How does it realize, wait, I've definitely been here before?
It applies a secondary algorithm to compute a similarity measure. It might use a bag of words approach.
Bag of words. Is that related to the SIFT fingerprints?
Yes. It's a collection of those SIFT visual fingerprints we mentioned earlier. It constantly stores these visual fingerprints of every place it has been.
Right.
When it detects a high probability match between the visual geometry it sees right now and a stored fingerprint from an hour ago, it forcefully overrides the accumulated movement errors.
It just tosses the bad math at 'em.
Exactly. It resets its location priors, pulling the two disparate ends of its internal map together and closing the loop.
It's the robot equivalent of a massive aha moment.
That's exactly what it is.
Like when you're lost hiking in the woods,
Yeah.
and you're starting to panic because nothing looks familiar, and then suddenly you see that weirdly shaped lightning-struck tree you passed 2 hours ago.
Yes.
Instantly, your entire mental map rotates and snaps perfectly into place. The panic vanishes. You know exactly where you are.
If we connect this to the bigger picture, researchers developing SLAM literally look to the biological brain for inspiration on how to solve these exact navigational problems.
Wait, really?
Yeah. In neuroscience, the hippocampus appears to perform incredibly similar computations. Mammals have specialized neurons called place cells.
Place cells.
And they fire only when we enter a specific location in our environment. This biological reality actually formed the basis for bio-inspired SLAM systems, like rat SLAM.
Rat slam, like the rodent.
Exactly, which mathematically models robotic navigation directly on the neural pathways of rodents.
That is wild. We are modeling advanced robotics on rat brains.
We are.
But I guess that makes total sense when you watch how effortlessly a rat can navigate a complex, changing maze without needing a spinning LiDAR laser on its head.
Right, they are incredibly efficient navigators.
There's also this concept in the source text of active SLAM, which feels very biological to me too.
Oh, active SLAM pushes the autonomy even further because traditional SLAM is somewhat passive.
Like a human drives the robot around, and the robot maps the environment as it is carried through it.
Right. But active SLAM studies the combined problem of the robot deciding where to move next in order to build the map as efficiently as possible.
So it's making its own choices.
Yes. It generally does this by calculating the entropy, which is the mathematical measure of uncertainty in its current map. It actively chooses the path that will provide the most new information to reduce that uncertainty.
It's literally exploring,
Yeah.
sniffing out the unknown edges of the map.
Just like a biological creature would.
So we've gone from dense Bayesian math to factor graphs to rat brains and shoe sensors. But let's bring this all the way back down to earth for you listening. Where did this technology actually originate, and where is it hiding in our everyday lives right now?
Well, the foundational concepts trace back to a 1986 paper by researchers Smith and Cheeseman. They were studying the representation and estimation of spatial uncertainty.
1986, so a while ago.
Yeah, but the field really solidified in the early 1990s. A research group led by Hugh Durant White pioneered the core mechanics, and he actually coined the acronym SLAM in a 1995 paper. They proved that absolute mathematical solutions to this problem exist in what's called the infinite data limit. And just knowing that a solution was theoretically possible motivated the entire robotics industry to start searching for computationally tractable approximations that could actually run on real hardware.
And that search culminated in a massive turning point in the 2000s, right?
Yeah.
The DARPA Grand Challenges.
Oh, yeah. DARPA, the U.S. military's research and development agency, held these highly publicized autonomous driving competitions in the Mojave Desert.
I remember seeing videos of those early ones. Cars just driving into ditches.
Yeah, because previous attempts at autonomous vehicles often tried to be deterministic. They wanted absolute truth, and when their sensors hit an anomaly, they just froze or crashed.
Enter SLAM.
Exactly. A researcher named Sebastian Thrun led the development of self-driving cars named Stanley and Jr. By utilizing advanced SLAM systems, these cars embraced probabilistic guessing.
They weren't afraid to guess.
Right. They used the math we've been discussing to navigate the unpredictable terrain. And Stanley actually won the 2005 Grand Challenge, which thrust SLAM into worldwide attention.
The trajectory of this technology is staggering to me. The exact same computational breakthrough that won a multi-million-dollar military DARPA challenge, navigating a robotic car across the harsh Mojave Desert, is now quite literally sucking up the dust bunnies under my living room couch.
It's true. Consumer robot vacuums use this exact tech to map our living rooms.
It's amazing.
And its application goes far beyond vacuums. If you use augmented reality on your phone, you are utilizing SLAM. Google's R-Core platform, which replaced an earlier project called Tango, uses a technique called maximum a posteriori estimation, or MA.
MAP estimation, what does that do?
Well, MAP estimation doesn't just make a random guess about where your phone is. It calculates the single most mathematically defensible reality based on your camera feed and motion sensors. It jointly estimates the pose of your phone and the position of the digital landmarks in your room.
That's why the Pokemon stays on the sidewalk when you move the camera.
Exactly. And if you put on a virtual reality headset like the Meta Quest 2 or the PQO 4, it relies on markerless inside-out tracking.
Which is?
That is pure visual slam happening in real time, instantly tracking your head movements so you don't experience motion sickness in VR.
So it is truly the invisible scaffolding of modern tech.
Oh.
But, circling back to the self-driving cars for a second, we talk about Stanley winning the DARPA challenge by mapping the desert on the fly.
Right.
Fast forward to today, we have autonomous vehicles testing on city streets everywhere. Are they just running incredibly beefed up versions of this same raw SLAM algorithm to navigate downtown traffic?
So this raises an incredibly fascinating modern caveat. Today, most commercial self-driving cars actually cheat at SLAM.
Wait, cheat? How do you cheat at a math problem?
By heavily simplifying the mapping side of the equation to almost nothing.
Really?
Yeah.
Yeah.
Modern autonomous companies use pre-collected, highly detailed map data. Think of Google Street View on steroids. These pre-recorded maps are annotated down to the granular level of marking individual white line segments on the asphalt and even the exact height of specific concrete curbs.
Oh, wow. So they already know the whole map before they even turn on.
Exactly. By already having a perfect, high-definition map of the city loaded into memory, they turn the incredibly complex simultaneous localization and mapping problem into a much, much simpler localization-only task. The car just uses its active sensors to figure out where it is on the pre-existing map and tracks moving objects like other cars and pedestrians at runtime.
So they aren't actively mapping the geometry of the world as they drive. They're just double-checking their sensor homework against an answer key that was already provided to them.
That's the reality of commercial autonomy today. And in outdoor applications, highly precise differential GPS sensors can also almost entirely remove the need to map the environment.
Because the GPS just tells it where it is.
Right. The GPS data provides such sharp location likelihoods that it absolutely dominates the Bayesian inference calculations.
But there has to be a catch to that.
Oh, there is a dangerous catch to relying on that. GPS can fail. It can lose signal in urban canyons, or it can be deliberately jammed or taken offline entirely during times of military conflict.
Right.
So for true, resilient autonomy, especially in defense, search and rescue, or emergency robotics, relying purely on GPS or perfectly pre-recorded maps isn't enough. Raw SLAM remains absolutely critical.
Wow. We've covered an incredible amount of ground today. We started with the classic chicken and egg paradox of needing a map to navigate, but needing to navigate to build a map.
The endless loop.
Right. We explored how Bayesian probabilities and algorithms like GrassLAM solve this by treating wheel movement as just another fallible sensor, pulling the map together with mathematical rubber bands.
Yep.
We shined a stadium floodlight on LiDAR, talked about fusing audio and visual sensors to track moving objects, and saw how loop closure mimics the aha moments of the biological hippocampus.
It's quite the journey.
It really is. And finally, we track SLAM's journey from 1980s spatial uncertainty research to military desert races, all the way to the Roomba navigating your living room and the VR headset on your face.
Right.
It is truly the invisible geometry holding our autonomous world together.
It truly is. And, as we wrap up, I want to leave you with a final thought to ponder, building directly on that modern caveat about self-driving cars we were just talking about.
Right.
We just discussed how modern autonomous vehicles essentially cheat at navigation by using perfectly pre-recorded high-definition maps of our cities. But what happens if the environment fundamentally changes overnight? Say, after a massive snowstorm, a hurricane, or a major earthquake that shifts the very streets and drops buildings into the roads. If that perfectly pre-made map suddenly becomes a lie, can these vehicles seamlessly revert back to pure raw SLAM to navigate the chaos? Or are we building a vast autonomous infrastructure that is entirely dependent on a perfectly static, unchanging world?